All right, so for this function, to get g prime of x, we already have x to the 2/3, so that's nice. By the way, this is equal to cube root of x squared, right? We don't need to know that. To get g prime, we really want to go from here, x to the 2/3. And we get 2/3 x to the negative 1/3 power, also known as 2/3 cube root x. All right, so that's our derivative. Now, let's look at the graphs. So basically, we're just trying to understand what is going on with these graphs. So I'm looking at this graph. I'm going to get the light a little bit better there. That's f of x, 2/3 x. Here comes g prime of x. So g of x has this, like, what does it have? It has this pointy part here. What was I going to say about that? Yeah, is there a hole there? Is there a hole at 0, 0? No, because the cube root of x squared is just 0. So g of 0 is 0. There's no hole in the graph. But g prime clearly has a vertical asymptote, right? And in fact, it's going to negative infinity on one side, positive infinity on the other side. So g prime doesn't even exist as a limit there. G prime doesn't exist as a limit. So one thing to remember is that the derivative is a limit. And that limit from the right and that limit from the left are going to positive infinity and negative infinity. So again, the derivative g prime doesn't exist. So we're looking at another way that g prime doesn't exist. So I have that one on Desmos 2. And that one's kind of interesting. So like what it has is this sort of really pointy area. See how pointy it is? No matter how I zoom in on it, it's pointy. It doesn't get flat no matter how I zoom on it. All right, it's pointy. So that type of a feature has a name that you might not have known before. What feature does g of x have at x equals 0? That thing is called a cusp. So cusp means a pointy thing like this, or it can be like this. A cusp can also be that I'm going along like this and then I take a sudden dive, right? So the idea is I was having a certain slope and then I radically changed slope. So it could even be like I was going at a slope like this and then I went like that, right? These are all examples of cusps. And all right, so what's f prime of 0? So if I try to do, it's g, g prime of 0. So that was kind of a, hopefully you answered the correct question, which is what is g prime of 0? All right, g prime of 0 is, g prime of 0 is 2/3 cube root 0, so that's undefined. Right. So basically we're looking at another reason why g prime might not exist. So at x equals 0, g prime of x does not exist. So we can say g is not differentiable at x equals 0. And we can say g is differentiable on negative infinity to 0 and 0 to infinity. All right, g is differentiable everywhere else because here's the derivative, it's 3 over a cube root of x, and I can evaluate that for any real number x except 0. So that's why we know g is differentiable on negative infinity to 0 union 0 to infinity, because here's the derivative and it's well defined. All right, so yeah, well, let's take a little bit closer look as to, this question why. Why is the derivative non-existent at a cusp? So if we look at a cusp carefully, so here's our cusp. All right. So think about the fact that g prime is equal to the limit as h approaches 0 of g of x plus h minus g of x over h. Of course, I could say f, but I was talking about the function g, so let's just keep with that, and I'll probably mess it up. All right, so think about What happens when h is positive? When h is positive, and we're thinking at x equals 0, okay? Then when h is positive, then x plus h is over here to the right of 0. But when h is negative, x plus h is less than 0, all right? X being 0 in this case, all right? So remember that the x plus h, if h is negative, you're talking about points to the left of x. And then if h is positive, you're talking about points to the right of h. So what happens in these two different cases? Well, anywhere that I'm looking over here at f of x and f of x plus h on the right, I'm going to have a positive slope. All right, so the slopes over here are positive. But if I'm looking at a negative h, any slope that I look at over here is going to be negative. So these are all negative slopes. So we could say something like the limit as h approaches 0 from the left of f of x plus h minus f of x over h is less than 0. And the limit as h approaches 0 from the right of f of x plus h minus f of x over h is greater than 0. And since the limit from the left is less than 0, the limit from the right is greater than 0, it follows that the limit as h approaches 0 from the left and the limit as h approaches 0 from the right are not equal. Therefore, g prime, the limit as h approaches 0 of g of x plus h minus g of x over h, does not exist. But so g prime does not exist. All right, so this is why conceptually g prime does not exist, and of course this is why mathematically g prime of 0 does not exist. But so basically we've now seen two different cases where the derivative might not exist. One is where the function has a vertical tangent. All right, let's just draw this vertical tangent. Just put it down here or something. Vertical tangent. Function has a vertical tangent. All right, the other way that the derivative might not exist is f has a cusp. All right, your book, by the way, distinguishes a cusp in a corner, where a cusp is curvy point and a corner is straighty point. However, I personally never use this word corner because it's not qualitatively different from a cusp. So I just call them both cusp. There's no reason to distinguish them. All right, so now we've seen two cases where f might not be differentiable, or a function might not be differentiable. Is there a third? Yes, there is. We'll do that next.